All right, question 2 on the 2019 test gave you this table and gave you this equation. That equation doesn't show up till part C, so we won't worry about it until then. But in the beginning, the velocity of particle p moves along the x-axis given by the differentiable function. That's going to be key, where v of p is measured in meters per hour and t is measured in hours. I'm going to go ahead and put that up here, t measured in hours, and then v of p is measured in meters per hour, just to make sure that we're seeing those units. Selected values are shown in the table. Part A, justify where there must be at least one time t on the interval from 0.3 to 2.8, where v prime, which is the acceleration, equals 0 meters per hour per hour. So we are only looking at t values between 0.3 and 2.8. So we essentially want to know or want to show that there's guaranteed to be a time where the derivative equals 0. Well, if I want to guarantee a derivative equaling something, that sounds like a theorem that we have called the mean value theorem. To the mean value theorem, recall there are 3 things that you need to use if you're going to, or need to have if you're going to use the mean value theorem. Those 3 things, once again, from first semester, your function has to be continuous. Number 2, your function has to be differentiable. And number 3, you must be on a closed interval. So we're definitely on a closed interval. The problem tells us that right there. T is less than or equal to 2.8, greater than or equal to 0.3, and so that interval is closed. Perfect. Continuous and differentiable. Well, the problem told us that v of p is differentiable, and differentiability implies continuity, so therefore we've got all 3 things taken care of as far as the mean value theorem is concerned. So according to the mean value theorem, the punchline of the mean value theorem says that as long as you have these 3 things, then there must be a time where the derivative of your function, v prime of t, has to equal the function value at b minus the function value at a all over b minus a. And so if we look at those values, our a and our b, that's the value that t is in between 0.3 and 2.8. And so if we plug in all the values that we have, this shows us that v prime is going to be equal to v of 0.3. And if I look at the chart, v of 0.3 is 55. Minus v of 2.8, which is also 55. All that's going to be over 2.8 minus 0.3. As long as that's not 0, which is not, that's not going to matter because the numerator is 0, and so the derivative must equal 0. But you can't just do that. You need to explain. It says justify why. So my justification would be because v is differentiable. That means it's continuous. It's continuous. There we go. And on a closed interval. So, by the mean value theorem, and you can abbreviate that as MVT, every calculus person knows that that's the mean value theorem. By the mean value theorem, v prime of t, which is also the acceleration, must equal 0. You could also use good old Rolle. It is technically Rolle's theorem, although we know how I feel about Rolle. It's not really a theorem, and so I'm going mean value theorem. But if you want to go Rolle, feel free. But those of you who want to do it the right way, you'd say mean value theorem. It's not wrong to say it the other way. 2 points. 1 point for showing that the slope's got to be 0, and then 1 point for your explanation. Should we get that point? Yeah, we see a lot of mean value theorem on the AP test. As long as you practice the stuff that I give you to practice, that should be an easy couple of points. But even if you don't get those points, there's a lot of other easy points in this problem, so fear not. Part B. Part B is one of those spots where we have some easy points. Part B Don't know why I did that. There we go. Part B asks us to use a trapezoidal sum with 3 subintervals to approximate the value of the integral. Notice we're only going from 0 to 2.8, so that 448 is not going to come into play at all. That's not part of it, so make sure you're only going from the limits that they give you, from 0 to 2.8. From here, you're just doing the trapezoidal rule. Area of a trapezoid is 1/2 the height times base 1 plus base 2, so your height is how far apart your intervals are. They are different. Remember, we've done these with tables before. You can't make them all the same. So the first interval is going to go from 0 to 0.3, so that's a height of 0.3, and then we'll use the two values of 0 and 55. And then my next interval, I'm going to add to that 1/2. We're going to go from 0.3 to 1.7. And that's going to be 1.4. And then multiplying by the two bases, 55 plus negative 29. And then finally, the third trapezoid plus 1/2. The separation there from 1.7 to 2.8 is 1.1. And then our two bases there, negative 29 plus 55. Again, we're not going out to the 4. The problem didn't define it that way. So that's all that we need to do, and then work it out. Let your calculator do the work, 40.75. And if we look at units, the units for that, if we were to integrate the integral v of p times dt, that would have to just be distance. And so that's going to be measured in meters, and so 40.75 meters. As far as points are concerned for this problem, unfortunately, it is that easy, and easy means not a lot of points. 1 point. You either get that or you don't. So don't make a mistake when you're doing the calculations, because you don't want to throw away that point because you didn't use your calculator, you did it by hand or something crazy like that. Next, part C. Part C gives us that second particle, so now we're going to be using that equation. So the second particle moves along the x-axis, and the velocity is given by that equation in meters per hour. Find the interval which the velocity of particle q is at least 60 meters per hour. And then find the distance traveled by that particle when the velocity of the particle is at least 60 meters per hour. So two different things going on here. So the first thing that we're going to do, part C, I'll put it right up here, is we're going to figure out when the velocity of q is greater than 60. And so we're going to take that velocity equation, v of q, and we want it to be greater than or equal to 60. I'm going to manipulate that equation when I punch it on my calculator. What I'm going to be punching on my calculator is the v of q equation minus 60. That way I'm only looking for when is that above the x-axis. That's pretty easy to find. I can just find the zeros using my calculator. You should find 2 times where that is where it's above the x-axis. It starts being above the x-axis at time equals 1.866, and it's above the x-axis until time equals 3.519. Okay, so it's between those 2 times. That's not solving it. Between those 2 times is when the velocity is greater than 0. And so we want to know, after that, what is the distance that it traveled over those times. And so if we want distance, the distance that we're going to travel, we just have to integrate the velocity equation. And so the distance that we're going to travel is going to be the integral from 1.866 to 3.519. V sub q of t, not v of t minus 60. That was something that a lot of students last year, they used the minus 60 equation. They used this. Don't use that. That's not the velocity. The velocity equation is just v. Make sure you are only integrating v, not v minus 60. You'll get a totally wrong answer. And so when you punch that on your calculator, you should get 106.1 meters. Points for part C. It's a pretty easy section, and so there's not a ton of points. There are 3 total points. If you came up with these t values, that's a point. If you knew that you needed to integrate the velocity, that's worth a point. And then getting the right answer with units is a 3rd point. I think that's 3 points we can count on. Finally, part D. Part D, we're going to use both pieces of information, both P and Q. In part D, it says at time t, particle Q is at position negative 90. Using the result that we found from part B and the function from part C, approximate the distance between P and Q at time equals 2.8. Okay, well, we already have part of this. I know where P is. I know where the particle is, for P, or at least I can I've estimated that already. That's from part B. Part B showed us by doing the trapezoid rule that the distance that P has moved, where particle P is 40.75 meters. And so that's locked in. Done. We don't do anything with that. To figure out where Q is at, we can figure that out the same way. If we look at what we did with P we integrated, but we couldn't integrate it. We had to estimate it with the trapezoid rule. But essentially, we found the integral. It also says in the problem, if you look at the problem, I don't have it here, but it says particle P is at the origin at time equals 0. So this 40.75 is how far it traveled, but since it started at the origin, technically I would add on where it started plus 0, but by adding on plus 0, it still stays at 40.75. So I'm just going to give it the 40.75 meters and be done with that. For Q, it's going to be the same thing, but it didn't start at 0. Part D says it started at -90. Okay. So I'm going to take -90 and then I'll add to it the integral from 0 to 2.8. Now this integral, because I have a calculator I can do, I'm integrating the velocity of Q, the equation that we were given, and that you just punch up on your calculator, and then don't forget to subtract the 90, and when you do that, you'll get 45.94 meters. But don't stop there. That's not what the question asked. Our question asked us how far apart are these, and so to figure out how far apart these are, we simply can take where the particle is at Q and subtract where the particle is at P. We have both of those values up there. If we subtract those two, we get 5.19 meters. That's how far apart these two particles are. Points for this, we get 1 point for knowing that we will have to integrate V of Q. You get 1 point for figuring out the 45.94. You don't get anything for 40.75 because you already got points for that in part B, so there's no need to give you points for that, and then you get 1 point for the answer of 5.19. This is a problem that is pretty consistent on the AP test. They love to give you a table and love to ask you to do LRAM, RRAM, MRAM, or trapezoid, and then do some other things. And so notice we did that. In part B, we did the trapezoid rule, and then we did a few other things. Those things are different from time to time. Mean value theorem does appear a lot, so all this that we did in part A, that's pretty consistent. We tend to see that a lot on the AP test. They also like to compare two things, and so we could see things like what we did in part D, comparing the two distances. All of those are very, very common. We will see those again and again as we look at other tests. But otherwise, these 9 points are something that I'm pretty confident that we can do. And I'm, again, not sure exactly how they're going to do the AP test. I know there's going to be 3 questions. This one is usually a guarantee, but at this point, I'm not sure. I would bank on this one being close to a guarantee. Trapezoid rule is something that they love to test, and so I would count on a problem like this. This is something that I would definitely focus in on. But otherwise, there's everything there, and look forward to our next video for problem number 3.